This week we're going to be discussing just a few things about the systems approach in this lecture. And we're going to talk about these 5 or 6 things. Why should we use the systems approach? Basics for biological growth, some important growth behaviors. Then we're going to analyze those growth behaviors using a simple stock and flow analysis. And there's going to be several key things for you to look for: positive feedback, negative feedback, steady state, and resource depletion. Now in this short slide set today, I'm not going to go over those, but those are well described in the text with some good examples. And then as a separate voice over narration, there's going to be sustainability from a systems point of view. So that's sort of like part 2 of the lecture for today. So the reason we use a stock and flow systems approach is we have so many environmental issues to address, and we need to find similarities. So that's one reason we can use a stock and flow systems approach to analyze many different types of environmental problems, from hydrology to ecosystems to sustainability. And another part is, what do we really want? What do we really want? Do we want to just fix stuff, or do we want to have a better world? And one of the pitches I'm going to make in this class is that natural capital, or the biological and ecological processes, may be a way to help us. So we really have to understand those better. And when we understand those better, that means we're trying to fix something, we're trying to improve our environment. We need to analyze those problems from different perspectives so we don't cause other problems. And the way we avoid causing unintended consequences or some surprises is to use different tools and different analysis approaches. And stock and flow systems is one of those. And you're going to see a couple others in this course. You're going to see network approach, and you're going to see a game theory approach, and looking at problems from what's uncertain and what's known. That's another way to avoid some of these problems. So again, just using the stock and flow approach on its own won't help us avoid the surprises that we might bump into, but as one of many approaches, it can help us avoid those unintended consequences. So first we're going to talk about biological growth, and this is mainly just a few definitions that we're going to use. And biological growth depends on resources, nutrients or light, or could be water in the soil that's used up. So if growth depletes that factor, then that's a resource. However, it's a condition if growth doesn't deplete it, but it's important for the growth rate and success of the organism. So for example, temperature. Organisms don't use up temperature, or fish in the ocean don't use up water, so that's a condition for them, because if they're out of the water they don't grow, but they don't use it up, whereas a tree uses up water. So you can't say something is a resource or condition just based on what it is. You have to know whether in that particular environment it's either depleted and it's a resource, or it's just a factor that affects growth, and then it's conditioned. And the other major aspect of this is the amount of active biological material growing. So you have a certain amount of biological material. If it has plenty of resources and the conditions are right, it's going to grow very well. So we're going to look at this with 3 growth models, and look at, by that model, use of the term model, I mean patterns of population versus time. These are descriptions of that pattern of growth of population versus time, and we'll call that a model of how the population grows. So the first is what's called the logistic, and I put this in quotes because it's a particular underlying equation that generates a curve that looks very similar to the growth of many populations if you follow population versus time. It's also called sigmoidal, or there's other names for it. But if you look at this particular growth curve, at A you need some population to start reproduction. That's beyond the scope of this class to explain that to you. But then as it goes through B and up into C, you have exponential growth, but then the resources start leveling off, or it gets too crowded. At least resources start being depleted, or it gets too crowded, and that's where you get this change from an exponential growth to a growth that's slowing down. And the growth rate, that is the change in population per time versus population. That's the growth rate. The growth rate at any time here going from C to D to E is slowing down. And finally at E, it's slowed down to 0, and that means no net growth. There's maybe birth rate equals death rate, or maybe if it's a single population, the population is actually at 0 growth rate. But this is where there's no increase in the population. So that's the logistic growth model, or sigmoidal. It's very useful in talking about many populations. Are they in this phase down here? Are they starting to level off? That's an important aspect of looking at it with this underlying model. Now another model is just exponential. We talked about this before in class. During a phase when you might call exponential growth, it's not slowed by any resource limitation. So the growth continues at the same growth rate. That is population change per time over the population. And so that ratio of new population that comes up, the ratio of the new population that comes up in each time point is the same, but the actual increment gets larger and larger as you have more and more population, because there's more population to change. And this can't continue forever, because we know eventually it's going to bump into some sort of space or material resource limitation. But during a particular phase of growth, we can really describe something as being an exponential growth. And then finally, another model that will come up in this course is this idea that we need a minimum viable population. So what we're describing here is that there's a population that's too low to overcome the losses or the reproductive inefficiencies at low densities, and below that level, below that population, instead of it increasing, it's going to decrease. And then above that minimum viable population, above that barrier, population will increase. So later in the course, when we talk about corridors or populations that are separated, this is really sort of an important piece of that we need to keep the population at a reasonable size so it can reproduce. Okay, here's some examples of other growth patterns that are very, very informative. One is we might see a damped oscillation, such as you see on the left here. This is an example from some data from sheep that were grown, and as they grew up in a resource-rich environment, they grew very fast, but then they overshot their carrying capacity, that they're eating the grass faster than it can be replaced. There was a die-off or a decrease in the population as their birth rate was less than the death rate. It went below the carrying capacity and oscillates around this. So this is a damped oscillation where the population homes in on some sort of carrying capacity. And in this case, that would mean that the growth of the grass and the other resources for the sheep kept up with the sheep growth. An example of a boom and a bust is the reindeer or caribou on Pribilof Islands, and they were introduced in 1910, and they took off and they grew very well during this period of time until they had totally depleted the food source. And the food they ate was lichen on rocks. It's very hard to, the lichen grows very slowly. So they start out with a very large stock of food to eat, but when they ran out, the population was so high that they had stripped the rocks bare. Really wasn't any food. There was a massive die-off due to sickness and starvation from those caribou. So this is boom and bust, overshooting by such an extent that when the population does crash, it crashes hard. So you can see, it'd be very interesting to know if populations of natural resources were going to behave nicely and oscillate around some sort of idea of a carrying capacity, or were they going to shoot up so far they decrease their resources beyond the level that can be replaced. So the systems analysis of growth patterns is, again, this material is covered in Chapter 6, and I think that's an important place so you can just sort of study that, and again, look for these key concepts. Positive feedback is when the amount of the stock, that the inflow to the stock increases as the stock concentration is higher. Negative feedback is with a higher stock concentration, it inhibits the inflow of, in the production of that stock. So positive feedback, good example of that, just like exponential growth. Negative feedback is a good example is that of the leveling off phase of the logistic growth. Steady state, that's when the birth rate equals the death rate, or when the input equals the output. And resource depletion, that's an example when the population would decrease rapidly because there was no resource available. So now, for another example, go to the week 4, part 2 on systems view of sustainability, and I'll walk you through what we might look at from a systems view.